Have you ever seen a massive cruise ship and just wondered? I mean, how on earth can this giant chunk of metal float when a tiny little pebble sinks straight to the bottom? It feels like it shouldn't work, right? Well, it's not magic. It all comes down to a really cool, simple idea in physics. And today, we're going to unlock the secrets of buoyancy. Okay, so to really get this, we're going to start with a puzzle, a paradox that seems to break all the rules. Think of it as a classic heavyweight mystery. And don't worry, we're going to solve it together. So here it is. Picture this, a 50,000-ton steel ship just chilling on the water, floating like it's no big deal. And then you have a tiny stone, plunk, sinks in an instant. So what gives? What's the hidden force at play here? Well, the answer isn't magic. It's actually all about a constant battle that's happening right under the surface. And that's where we find our answer. The secret to this whole floating paradox is a constant tug of war. It's a battle between two opposite forces, and it's happening to any object that's in a fluid. And yeah, that means water, but it also means the air around us. So let's look at the two teams in this tug of war. On one side, you've got weight. That's just gravity, right? Pulling everything down, always. And on the other side of the rope, we have the buoyant force. This is the secret weapon, the upward push that the liquid gives back. It's literally the water pushing up. And the winner of this tug of war, well, that decides everything. If weight is stronger, the object sinks, game over. But if the upward push of buoyancy is stronger, or even if it's just a tie, the object floats. It's a simple idea, but it leads to the real question, right? What decides how strong that upward push actually is? For that answer, we actually have to travel back in time, like more than 2,000 years ago, to a super smart Greek mathematician. It's time to reveal the secret rule he discovered, the key to solving our entire paradox. And here it is. It's called Archimedes Principle. Now, I know, that sounds a little formal, a little textbooky, but the idea behind it is so simple and honestly pretty beautiful. All it says is this. The upward push an object feels is exactly equal to the weight of the water it pushes out of the way. Let's break that down, because it's kind of like a chain reaction. So step one, an object plops into the water and pushes some of that water out of the way. We call that displacement. Step two, that water it pushed aside, it has weight. And step three, the water around the object pushes back up with a force that is exactly equal to the weight of the water that got moved. That upward push, that's your buoyant force. Okay, so this gives us three super clear outcomes. Rule number one, if the buoyant force pushing up is equal to the object's weight pulling down, you float. It's a perfect balance. Rule two, if the buoyant force is less than the object's weight, gravity wins and you sink. And rule three, which is pretty cool, if the buoyant force is greater than the object's weight, it doesn't just float, it actually rises. All right, so theory is one thing, but let's put this principle to the test in the real world. And what better way to do that than by finally solving our big heavyweight mystery? First up, the stone. Let's go back to that little stone. Why does it lose the tug-of-war so badly every single time? Well, it all comes down to density. A stone is super dense. It packs a whole lot of weight into a tiny little package. So yeah, when you drop it in water, it does push a little bit of water out of the way. It gets a small upward push, but that push is it's nowhere near strong enough to fight against the stone's heavy weight. Gravity just completely overpowers it, and splash, it sinks. Okay, so what about something you see floating all the time? Think about an ice cube in your drink. I mean, it's just frozen water. So what's the deal? Why does it float? Again, the secret is density. It's a weird quirk of water, but when it freezes, it actually expands. This makes ice less dense than liquid water. So the ice cube only has to sink part of the way to push aside just enough water to perfectly balance its own weight. The upward push equals the downward pull. The forces are in perfect harmony, and it floats. Okay, the moment of truth has arrived. Let's take everything we know now and finally solve the mystery of that 50,000-ton steel ship. So here's the big secret. It's not about the steel, it's about the shape. A ship is basically a giant, cleverly designed hollow bowl. Yeah, the steel itself is super dense, but the ship is mostly air. That hollow shape means its average density is actually way less than you'd think. Because it's so huge, it pushes an incredible amount of water out of the way. And all that displaced water creates a massive upward buoyant force. a force big enough to perfectly match the ship's enormous weight. It's the ultimate tug-of-war tie. You know, you've seen this yourself, maybe without even realizing it. The next time you get into a bathtub, watch the water level. See how it rises? That's you. You're displacing that water. And if you could somehow scoop up and weigh just that extra water that you pushed up, its weight would be exactly the same as the buoyant force that's holding you up a little bit in the tub. Now, it's easy to think this is just a rule for things in water, boats and bathtubs. But this principle is way bigger than that. It's not just water. It applies to every fluid. And yep, you guessed it. The air all around you is a fluid too. That means this exact same battle, this tug of war between weight and buoyancy, is happening constantly, everywhere, even in the air. Just think about a helium balloon. It takes up space, right? So it's displacing a bunch of air. But here's the thing. Helium is way, way lighter than air. So the weight of the air the balloon pushes aside is actually more than the weight of the balloon itself. In this case, the buoyant force from the air is the clear winner of the tug of war. And what happens when buoyancy wins? The object rises. And for those of you who like to see the math behind the magic, here's a quick peek. This is the formula scientists use. Don't let it intimidate you. It's actually just a neat summary of everything we've been talking about. See? You've got the fluid's density, gravity, and the volume of fluid displaced. It's all right there. Okay, so let's do a super quick recap of the key ideas. We've got the buoyant force, that's the upward push from the fluid. We've got displacement, that's the fluid getting pushed out of the way. Whether something floats or sinks all comes down to that battle between weight and buoyancy. And a really good shortcut, just compare the object's average density to the fluid's density. So the next time you see a giant ship sailing by, here's what you'll know. 3 key takeaways. Number 1, everything is in a constant battle between its weight pulling down and buoyancy pushing up. Number 2, that upward push is always equal to the weight of the fluid it displaces. And number 3, and this is the big one, it's not just about what something's made of. Shape and average density are the real game changers. And with that, I'll leave you with one final question to chew on. Now that you're an expert on buoyancy, think about this. What single object could you add to a small, floating boat that would guarantee it sinks? Think about the forces, think about displacement. The answer might be a little more clever than you first think.